This week, we will feature glass making, the secrets of ceramics, and the architectural possibilities of glass. You're at home, glasses on your nose and a glass in your hand. You turn on a light bulb, turn away from the television set to glance out the window. But not for too long. Glass is everywhere. Its applications are virtually limitless. But do you know how it is made? Glass is made from sand, one of the most abundant substances on the surface of the Earth. However, its properties are radically different from sand. Indeed, glass is not a true solid, but a viscous liquid which stiffens when cooled. The miracle of glass occurs in the fire of a furnace. In a refractory earthenware crucible, the glassmaker prepares a mixture which contains 60 to 75% of siliceous sand. This sand is mainly composed of silicon dioxide, or silica. This compound forms crystals, extremely well-ordered atomic networks that are united by regular bonds. To this mixture, the glassmaker adds various components called fluxes. These can be soda, potash, limestone, or oyster shells. These components are used to improve fusion, which occurs around 1500 degrees Celsius. They also prevent the glass from becoming too fluid at high temperature. The glassmaker heats the mixture. The heat causes the sand's crystalline structure to break. All the components react among themselves, forming a quite disorderly assembly. It is to this irregular structure that glass owes its amazing properties. Among others, it can be shaped at will. The molten glass is now ready for blowing. The glassmaker gathers a small lump of the molten glass on his long hollow rod. He is said to gather the parison. He then blows into the rod until the red lump inflates and becomes a bubble. While turning the rod continuously, he shapes the matter with a metal, iron, or wooden slab called a marver, or with his hands, using a wet newspaper. On contact with the air, the glass gradually hardens as it cools. It is reheated in a furnace so it can continue to be modeled until it reaches the desired shape. At the end of this operation, however, the glass is still fragile. A final firing will give it its hardness and strength. This process helps the glass to withstand thermal shocks, which would weaken it. Since it is no longer in fusion, but just reheated, it is better able to withstand the change to the ambient temperature. Another technique consists of using a propane torch to shape the article. By setting the molecules in motion, the flame makes the glass malleable and sticky, yet without melting it. Glass can also be worked cold. It can be engraved with pointed instruments or such chemical agents as hydrofluoric acid. Unlike the glassmaker, the stained glass window maker seldom etches his piece. What interests him is to modulate light by varying the colors and textures of the glass. To do this, the artist uses previously colored pieces of glass. He may also color them himself, using a chloride or silver sulfide-based paint, which act by cementation. a chemical reaction between the components in the glass and those of the silver salt. Cementation allows the paint to adhere to the glass definitively, yet remain transparent, a much prized quality for stained glass windows. To make a stained glass window, the oldest and most common technique is the lead technique. The glazier starts by studying the play of light in the room in which the stained glass window will be installed. He then makes a series of small-scale models of the work, 1/10 the size. Next, using a tracing, he makes a cartoon, a colored sketch of the full-size window. Each sketched piece is numbered. Once cut out, it is used as a pattern to cut the glass. A puzzle of glass pieces is thus created. The glazier can now move on to the next step, which consists of fitting each piece of glass into channeled lead strips. The lead strips are then fastened in small points and soldered together. They are then covered with putty to prevent water from seeping in. At this point, the stained glass window is ready to be installed. Its beauty will now depend on the quality of the surrounding light where it is installed. The old stained glass windows were not merely sheets of colored glass. They told whole stories with a beginning, an end, suspense, and even a moral. The art of glassmaking is very ancient indeed, but before perfecting that art, our forebears had already mastered a close relative, ceramics. Like glass, ceramics come into existence by fire. However, ceramics are not made with silica, but most often with a clay base. Clay is a rock essentially composed of aluminum silicates. When these components are heated at high temperature, the silicate structure breaks. Yet after gradual cooling, minuscule crystals reform. This crystalline structure is what gives ceramics their hardness and resistance. There are many types of ceramics. What differentiates them are the quality of the raw materials used and the temperature at which they are fired. These two factors influence the degree of organization of the crystals, which, in turn, determines the quality of the finished product. A very pure kaolin clay, for example, fired at 1400 degrees Celsius, will produce fine china. On the other hand, ordinary clay fired at 1100 degrees Celsius is used to make bricks or floor tiles. Conventional ceramics often start with a preparation of clay combined with other raw materials such as feldspars and quartz. These raw materials are ground and mixed with water, producing a suspension called slip. Once filtered and pressed, the slip is packed in the shape of cylinders. At this stage, the method of fabrication will depend upon the application intended. To make sinks or tureens, for instance, a molding technique is used with porous molds generally made of plaster. The slip cylinders are first cut and mixed with water to form a liquid paste. This is poured onto the walls of the porous mold, which absorbs the liquid. After drying, the consolidated article is fired. this is the most important phase of the production. The firing is what will determine the final characteristics of the product. To make simple shaped articles in large quantities, tiles or plates for example, the process used is called dry pressing. In this case, a very fine powder is used instead of a damp matter. The powder is obtained by shredding the slip cakes in a warm atmosphere. The powder is placed into the molds. Pistons exerting an even pressure over the entire piece then compress it. This prevents distortion. The article is then fired in a kiln. The next step, called glazing, gives the piece its aesthetic and functional qualities. A glaze is a coating with a composition similar to that of glass. After firing, it waterproofs the piece and makes it shiny and solid. Glazing can be done by dipping the ceramic piece into a tank of liquid glaze. For larger pieces, spraying is preferred. Glazes can also give ceramics color when certain substances are added to them. The uses of ceramic materials continue to grow. Their fabrication from the purest and finest powders constitutes a veritable revolution. The ceramics produced are stronger than steel and capable of withstanding very high temperatures. They are achieved by mixing, in precise proportions, powders whose components have been carefully controlled and selected. This painstaking work is done by specialists using sophisticated image analysis and electron microscopes. These processes enable them to count the number of grains and describe their morphology, and to determine the mineral composition of the powders. Through rigorous selection, ceramics can be made for medical purposes. New ceramic materials can, for instance, be used to make hip prostheses. These fine ceramics are stable and particularly well tolerated by the organism and will not cause inflammations due to rubbing. Modern ceramics are as efficient as they are unobtrusive. In the kitchen, for instance, alumina joints are better sealed and the taps quieter than the conventional models. Zirconian knife or scissor blades are very hard wearing, though extremely fragile. In the automobile trade, the mufflers of some cars are already fitted with honeycomb ceramics. Research is even being conducted on ceramic engines. Such engines would be about 40% lighter and withstand far higher temperatures than conventional engines. More fuel efficient, less polluting, and more resistant. They may well power many vehicles in the years to come. The list of applications for ceramics is growing by the day. Radar components, protective shields for spacecraft, bricks. While ceramics are slipping into all sectors of technology, glass continues to make its way into our daily lives. One of its most daring areas of application is architecture. Owing to its transparency, glass has long been one of the preferred materials in architecture. But this property is no longer enough to satisfy today's architects. Glass now fulfills myriad technical functions. Since the energy crisis, for example, reflecting windows are much used, notably in air-conditioned offices, because of their solar and thermal insulation properties. What gives glass these properties is a fine layer of metallic oxides, either integrated with the glass or coating its surface. During the day, the oxide layer reflects part of the sun's heat-producing infrared rays outwards. Seen from outside, the window has a mirror-like appearance. At night, however, the opposite occurs. The oxide layer reflects back the infrared rays produced in the room, preventing the heat from escaping. Today, the glass used in architecture performs a number of functions simultaneously. Reflecting windows can also incorporate acoustic features, which often reinforce heat insulation. This is done by sandwiching a layer of air or gas between two pieces of glass. About 10 millimeters thick, this layer cushions the pressure exerted by sound waves. Noise is a complex series of sound waves created by the vibration of air molecules. In the normal temperature of a room, sound waves propagate at a speed of 340 meters per second. Double windows absorb the sound vibrations, thus curtailing their transmission. The same effect can be obtained by joining two windows of different thicknesses. Thanks to this simple procedure, the intensity of sound in a room can be cut by half. Moreover, the thin layer of air improves thermal insulation and provides energy savings of roughly 45% compared to a single window. That's why double glass partitions have become virtually standard in cities and countries where the climate is cold. Since today's windows have been made to any number of needs, aesthetic, thermal, acoustic, there is no reason why they can't be safe as well. This is a major problem since shattering glass causes severe accidents every year, especially with children. Laminated glass is one answer to that problem. Laminated glass is made by bonding two or several pieces of glass together with a film of polyvinyl butyryl, also known as PVB. The PVB film, less than 1 millimeter thick, is sandwiched between two plates of glass. The sandwich is then compressed between two pneumatic rollers to evacuate any air bubbles. It is then heated to bonding temperature under pressure in an electric autoclave. This softens the PVB. After 3 or 4 hours, the PVB is completely melted. Now completely transparent, the PVB serves as an adhesive which bonds the sheets of glass solidly together. If the glass does break, the PVB will contain the fragments and prevent it from shattering. 6 millimeter thick laminated glass is commonly used in schools and sports buildings, for example. Sometimes there is reason to reinforce windows even more. Certain bulletproof windows can be up to 10 centimeters thick. Tempered glass is another type of safety glass. Unlike conventional glass, when broken, tempered glass shatters into tiny pieces. These fragments, less than 2 or 3 millimeters in size, have no sharp edges, which reduces the chances of injury. To make tempered glass, a conventional sheet of glass is heated to 620 degrees Celsius and abruptly cooled in cold air. The resulting thermal shock weakens the glass, creating numerous less resistant areas over its entire surface. A mechanic shock will cause the glass to shatter all over. In addition to these technical functions, we now require that the glass used in modern architecture have aesthetic qualities. In this regard, the ultra-clear glass over the Pyramid of the Louvre in Paris is quite a technological feat. Although glass is naturally transparent, conventional windows tend to tarnish over time. This is because they contain ferrous ions. These ions react with the oxygen in the air, forming iron oxides. Iron oxides will eventually give glass a greenish color. In the case of the Louvre's pyramid, the problem was solved through special firing techniques, a well-guarded secret, which eliminate the ferrous ions. It is believed these windows will remain perfectly transparent forever. In modern architecture, glass is slowly replacing stone. Whether tinted or almost invisible, glass protects us against variations in temperature as well as from noise. It's without a doubt the only material that can boast such a complete range of functions. Scientists dream of a global window. That super window would encompass a lighting and heating system. It would vibrate like the diaphragm of a loudspeaker. And why not project your favorite program?